Hello everyone, this is Jaisal Desai. In this session, we will learn about query processing and optimization, which is one of the most important topic of database management systems. In this topic, we will study how the query in SQL format is processed and how the results are generated. So the query processing refers to a range of activities that are applied on the SQL query and generates the results. So we can think of it as a query processing black box which takes the query, which is in SQL format, do some activities on it and generates the results, which is nothing but the set of tuples. Now the steps involved in query processing are parsing and translation, optimization and evaluation. Now before we understand each step one by one, we must understand that the system does not understand SQL query. So the requirement here is to convert the SQL query into some form which the system can understand. And the more useful internal representation is based on extended relational algebra. So here there is a need of converting SQL query into extended relational algebra so that the system can understand. Or we can say the high level query is transformed into low level language. Now we will understand the concept through a diagram. So the query, the SQL query is transferred to parser and translator. Parser checks for the syntax and verifies the relation. Here verifies the relation means let's say an example. Let's take an example. It checks for the relation name in the query and the relation name in the database. So it checks whether the name of the relation in the query written by the DB is same as the name of the relation in the database, or DB has done some mistake in mentioning the name of the relation in the query. So it verifies the name of the relations as well as it checks for the syntax errors and forward it to translator if everything is correct. Translator translates the query into relational algebra expression and then forward it to optimizer. Optimizer collects the statistical information about the query like disk access time, CPU cycles, network transit time and many more. So in short, the optimizer calculates the cost of query and forward it to query execution plan. The query execution plan tells the evaluation engine how to execute the query step by step. So after taking that plan from the execution engine plan module, the evaluation engine takes the data from the database and generates the results. Now here in the next slide we will understand why this optimizer takes the statistical information, what is the need of this, and what is the main role of optimizer, what is the main role of execution plan and evaluation engine. So let's see, as I have already told you that parser checks for the syntax errors and verifies the relation. Now the query evaluation plan is nothing but the sequence of primitive operations used to evaluate a query. For example, it will tell the system go to the account relation, select those tuples where balance is less than 2500 and then project the attribute balance. So this is nothing but the query execution plan, and this plan is taken by the query execution engine. It will take this plan, executes the plan and generates the results. So query evaluation engine works based on this plan which is provided by the query execution plan module. So let's take an example. Select balance from account where balance is less than 500. Now we will understand the rule of optimizer. So this SQL query can be converted into more than one relational algebra expression. Here we can see the first one is the balance attribute is selected from the account relation, and then afterwards those tuples are selected where the balance is less than 2500. In the second one, first the tuples are selected with balance is less than 2500, and then the balance attribute is projected. So both these queries will give the same result, but their execution is different. So the rule of optimizer is to decide which query has the less cost, or which query takes the less CPU cycles, less CPU time, or less CPU disk access. Only that query will be selected and forwarded to query execution plan. So now we see that the query evaluation plans created during the query processing steps for a given query can have different costs. So the role of optimizer is to decide which query takes the less time, or it optimizes the query and then forward it to the next module. We cannot expect from the users that they write the efficient query which takes the least time, but this is the responsibility of the system to construct the query evaluation plan and minimize the cost of the query evaluation. So here comes the role of query optimization. The cost of query, as I said, involves nothing but the statistical information about the relations like relation size, index depth, disk access time, CPU cycles, etc. So now let's take an example. Find the names of all the customers who have an account at a branch located in Brooklyn. So here it is represented in relational algebra form. Here we have to use three tables. We have to join these three tables. Account is joined with depositor, and the result is again joined with the branch. And finally, from the resulted relation, those tuples are selected where branch city is equal to Brooklyn, and finally the customer name is projected. So here this query can also be written as in this form in extended relational algebra expression. Here first the selection operation is done. The tuples where the branch city equal to Brooklyn is selected from the branch first, and then the result is joined with the result of account cross depositor. So here we can see what's the difference. The difference is that the branch, let's say there are 100 tuples in depositor, 100 tuples in account, and 100 tuples in branch. So in the first query, the 100 tuples of depositor are joined with 100 tuples of account, and then the result is joined with the 100 tuples of branch. And whereas in the second query, 100 tuples of depositor is joined with the 100 tuples of account, and the result is joined with only the 50 tuples of this operation. Let's say from the branch relation which has 100 tuples, but it has only 50 tuples where the branch is equal to Brooklyn. So this expression from here to here, this expression will give 50 tuples. These 50 tuples are joined with the result of account cross depositor. So we can here see that the first query will result in the large intermediate relation, whereas the second query will result in the smaller intermediate relation. Now what is the meaning of intermediate relation? In the first query, the execution time will be not fast, but the execution time will be very large, because 100 rows are of depositor will be joined with 100 rows of account, and then the result will be joined with the 100 rows of branch. So it will take more time, whereas in the second query 100 rows of depositor are joined with 100 rows of account, but the result of this join will be processed with only the 50 rows of branch table. So this generates the this will execute faster as compared to the first query. Now we can we can see from the diagram also, 100 rows of depositor are joined with 100 rows of account, and the result is joined with the 100 rows of branch in the first query, and then the selection is done where branch city is equal to Brooklyn, and then finally the customer name is projected. Whereas in the second query, 100 rows of account are joined with 100 rows of depositor, but the result is joined with only the 50 rows of branch, because the selection is done in the earlier phase only, where branch city equal to Brooklyn. So, and then finally the customer name is projected. So this is the initial expression tree, and this is the expression tree after several transformations. Both are equivalent expressions. The equivalent expressions are nothing but the expressions which provides the same results, but the execution time is different. Now we see that the query evaluation plan involves two steps. The first step is generating the query or expression which is logically equivalent to the given expression, and then second is generating the cost of each plan. To implement the first step, the query optimizer uses some equivalence rules. The role of equivalence rules is nothing but to replace the expression of the first form by an expression of the second form, and vice versa. Both the expressions are equivalent, both the expressions will be equivalent, but the only difference will be of execution time efficiency. So here we will see some equivalence rules. For example, the first one, rule number 1, it says that the relation E1 is joined with E2 is same as first E2 is joined with E1. The second rule number 2 says that the E1 and E2 relations are joined, and the result is joined with E3 relation is same if E2 and E3 relations are joined first, and then the relation is joined with E1 relation. The third rule says that E1 and E2 relation are joined, and then the selection is done is same as if the selection is done from E1 first and the result is joined with E2. This is similar to the previous example which we saw, where the selection of branch city equal to Brooklyn is done earlier and then the joining was performed. The only condition is that the theta has attributes only from E1, like branch city is the attribute which belongs to only branch relation. Now we will see another example which involves three schemas: branch schema, account schema, and depositor schema. Branch schema has three attributes: branch name, branch city, and assets. Account relation has three attributes again: account number, branch name, and balance. Depositor schema has again two attributes: customer name and account number. So here we can see this is our previous example. Now we know that it takes or it applies rule number 3, where the selection is done and then the joining is done. Now let's modify the example and add one more condition: branch city equal to Brooklyn and balance is greater than 1000. So now we have to convert this relational algebra expression into optimized form. So applying rule number 2, we are now first joining branch and account first rather than joining account and depositor first. So this is the rule number 2, which says that joining E1 and E2, and then the result of E1 and E2 is joined with E3 is same as joining E2 and E3 first and then joining the result of E1 with the result of E2 and E3. So after applying rule number 2, our expression will look like this. So why we have done this? We have done this so that we perform the joining of branch and account first, and then after applying rule number 3, here we can see applying rule number 3, and with the change of few brackets, here we can see we are doing the selection first. We are joining branch and account relations, and from the resulting relation we are selecting only those tuples where branch is equal to Brooklyn and balance is greater than 1000. So let's suppose there are 10 rows where branch is equal to Brooklyn and 10 rows where balance is greater than 1000. So in total we get 20 rows because this is the end condition. Let's suppose that we get the result, it has 20 rows. So these 20 rows will be joined with 100 rows of deposit. Earlier what we were doing, we were joining 100 rows of branch with 100 rows of account and then joining 100 rows of depositor. Here we are joining only 20 rows with the 100 rows of depositor. So this is much more efficient. Now we can say that here we can break the selection into two selections. Further, we know that the branch city belongs to branch relation and balance belongs to account relation. So what we can do is we can break the selection. We can select branch city from Brooklyn, which gives 10 tuples, let's say, and we can select balance which is greater than those tuples where the balance is greater than 1000 from the account, and it gives suppose 10 tuples. So now we can see we have applied here perform selection early rule. So next you can see that 10 rows are selected where the branch are equal to Brooklyn, and 10 rows are selected where balance is greater than account, and then these 20 rows will be joined with 100 rows of depositor. So this is much more efficient than joining 100 rows of depositor with 100 rows of account and then 100 rows of branch and then doing the selection operation. So now these are the expression trees. Here we can see this is the expression tree where the selection is done later on, and this is the expression tree after several transformations where the selections are done earlier from branch relation and then from account relation, and then afterwards the joining is done with the depositor relation. Now we can say, or we have learned, that the different evaluation plans for the given query have different cost. The query having the least cost is selected by the optimizer. The query evaluation plan is generated by the evaluation plan module for that query only, and once the plan is chosen, the query is executed, evaluated by the query evaluation engine, and the results are generated. So I hope that I am able to make you understand about this query processing and optimization concept. I hope you all have understood this concept clearly, and if you have any doubts you can ask me anytime. This concept or this reference, I have taken reference of this topic, I have taken it from the this book, Database System Concepts, 4th edition. And now thank you very much for giving your time. Thank you.